Good evening, Carmarthenshire. This is all about a total eclipse of the sun. And what I'm going to be talking about is a little bit about why they happen and when they happen. And I'll be talking about an eclipse I experienced with a few friends back in 2006. And I'll be talking about where it was seen and in particular the experience of what it was like. And I'll finish with a little bit about future eclipses. So for those of you who get the bug and the idea that they'd like to see a total eclipse for themselves, I'll say a little bit about where you can see one in years to come. So firstly, let me make it quite clear that nobody should ever look at the sun without using either special eclipse glasses, if you're going to be looking at the sun, or special equipment. There are such things as solar telescopes, but never use ordinary binoculars or ordinary telescopes to look at the sun, except in the middle of an eclipse. And as the eclipse progresses, you should be using eclipse glasses to protect your eyes as the moon starts to cover the sun until the moon has completely covered the sun. So you should always use special regulated eclipse glasses to make sure your eyes are safe. So everybody should use eclipse glasses whenever eclipse is taking place. And everybody means everybody, whether you're young or whether you're old. And you could argue that everybody absolutely means everybody. Now, some dogs can really play this to advantage. Some don't quite have the same panache when it comes to wearing eclipse glasses. But kids and adults should take it very seriously and make sure you use the safety glasses until the middle of an eclipse where the moon completely covers the sun. Okay, safety lecture over. So the sun is interesting for a lot of different reasons. The surface temperature of the sun is about 6,000 degrees. But for some reason we don't fully understand the outer atmosphere of the sun, the so-called corona. It's a lot fainter, but apparently it's a lot hotter. 2 million Kelvin, 2 million degrees. So although there aren't many atoms in this part of the sun's atmosphere, they're moving very fast, which is why we say they have a very high energy or very high temperature. And this corona, this atmosphere of the sun, is so faint that it's not visible whilst the very bright disk of the sun is in the sky at the same time. So during the day, the very bright disk of the sun, which is dangerous to look at directly, that will completely wash out any hint of the rather faint solar corona, the atmosphere. But if the moon were to cover the disk of the sun and block out the glare of the disk of the sun, then we would be able to see the solar corona. And that's what most people want to see during an eclipse of the sun. Now, this is not to scale. This is just to remind us that there's an awful lot of matter coming off the surface of the sun. The sun at 6,000 Kelvin is producing a lot of atoms, a so-called solar wind, not wind in the way we understand the motion of air on Earth, but wind in the sense of atoms moving very fast coming off the sun. Some of those atoms make it past the Earth's magnetic field and hit the Earth's atmosphere. And any fast-moving particles from the sun that hit the Earth's atmosphere can produce aurora. Some of us might have been lucky to see some aurora recently. Usually it only impacts in the northern and southern latitudes around the Arctic Circle and the Antarctic Circle, but recently we've had magnetic storms which have distorted the Earth's magnetic field and produced particles raining down in the Earth's atmosphere at lower latitudes. But normally from the Arctic or Antarctic you would expect to see northern lights like this, perhaps every night or every few nights. Energetic particles from the sun hit the Earth's atmosphere and cause the glow of green or sometimes purple and sometimes red from the atoms in the atmosphere being excited by the particles from the sun. So these were pictures I took of the aurora when I visited Iceland about 20 or so years ago. And that's another view again of the aurora. For those that know the night sky, here's the constellation of Orion over on the left hand side, and there's the Seven Sisters cluster right in the middle. So you can see stars are still visible through even the brightest auroras in general. Now, of course, the moon itself is a very interesting object to astronomers. It can be fascinating to watch the moon night by night as the angle at which the sun hits the moon's surface will change night on night. So you can watch the shadows change, the shadows which delineate the craters and the seas and the mountain ranges that are visible over most of the surface of the moon. Night by night and almost hour by hour, you can see the shadows slowly change as the angle of the sun changes on the surface of the moon. And it can be quite fascinating simply to watch features on the moon. But in this context, when we're talking about a solar eclipse, the moon is simply an object which will block out the light from the sun. So we'll be seeing the dark side of the moon. It'll still be the closest near side, but it'll be dark because it'll be between us and the sun. And it will simply be an occulting disk. It's simply an object which fortuitously is just the right size to block out the light from the sun and show us the solar corona. Now, that particular piece of geometry, this is indicated on the left-hand side here, none of this is to scale. But bear in mind that in order to get a moon blocking the sun at the surface of the Earth where the cursor is currently pointing, we have to have this coincidence that the apparent size of the moon is just the same as the apparent size of the sun. In other words, they both subtend an angle of about 1/2 degree in the sky. And this is thanks to a coincidence that the sun is 400 times bigger than the moon, but it's approximately 400 times further away, as seen from the surface of the Earth. And therefore we have this coincidence that depending on exactly how far away the moon is from the Earth, it can block the disk of the sun. Now, most objects don't move in perfect circles, and so the distance from the Earth to the moon just does vary a little bit. Sometimes the moon is further away and sometimes the moon is a little bit closer, and so the apparent size of the moon in the sky does change, and sometimes it isn't quite large enough to block the entire disk of the sun. So if we imagine we're at this point on the Earth where the shadow is just seen coming to a point on the surface, if we imagine that's where we are, then if we're in the right place at the right time, we will see a total eclipse as the disk of the moon covers the disk of the sun. If we imagine that we were a little bit closer to the moon, or if you prefer, if you think of the Earth being fixed, imagine the moon being a little bit closer to the Earth. Doesn't really matter which way you think of it. If the Earth-Moon distance is a little bit shorter, then the moon will appear larger in the sky, so it will take longer to occult the sun, it will take longer to eclipse the sun, and so the total eclipse will last longer. Conversely, if we're a little bit further away from the moon, or for a person on the Earth, if the moon is further away, then we will get a situation where the disk of the moon is simply not large enough to completely cover the sun, and then we get what we call an annular eclipse. If we think about what that looks like, the situation here with a total eclipse where we're at the closest point to the Earth, then the disk of the moon will appear larger than the disk of the sun, and so it will be able to easily cover the sun, and it'll take a while for the motion of the moon to cover the sun, and hence the eclipse will last longer. For the middle position, the disk of the moon and the disk of the sun are basically the same size, so that will give you a very short eclipse, because as soon as the moon has covered the sun, it'll start to move away again and the sun will be exposed. And in the third situation, when we are further from the moon, or the moon is further from us, the disk of the moon appears quite small compared to the disk of the sun, and so it won't be actually large enough to at any point cover the entire disk of the sun. So if we imagine the moon moving as it does around the Earth, in the first case it'll easily cover the sun for quite a few minutes. In the middle case, the moon will just cover the sun for perhaps a second or two, so a very short eclipse. And in the bottom case, when the moon is further away from the Earth and hence a smaller disk, it'll never be quite enough. So even when they are completely lined up, we'll get a so-called annular eclipse, because there will still be a ring of light from the sun coming around the edge of the moon. so an annular eclipse because of the ring of fire that is seen in the middle of the eclipse. So why don't we get an eclipse every month? If the moon takes a month to go around the Earth, why is it that we don't see an eclipse every month? It's because the moon is going around the Earth in an orbit which is tilted relative to the plane in which the Earth goes round the Sun. So this large plane in the centre here is the plane of the Earth going around the Sun. And this is a little bit exaggerated, but the plane containing the moon going around the Earth is tilted by about 5 degrees or so. So you can see on the right hand side here, for instance, here a new moon occurs, but its shadow misses the Earth because the shadow is above the Earth, because the new moon occurs because of the tilt of the moon's orbit relatively high compared to the plane of the Earth's orbit, and so the shadow of the moon doesn't hit the Earth, so no eclipse occurs. And similarly on the other side, on the left hand side here, the tilt of the moon's orbit is approximately the same, and here the new moon is low compared to the Earth, and so the shadow of the moon misses the Earth because it goes further south than the South Pole. If we want the shadow of the moon to hit the Earth, what we need is for this line, the line that defines the intersection between the moon's orbit, the plane of the moon's orbit, and the plane of the Earth's orbit, that particular line is called the line of nodes. A node is the point that I'm showing here with the cursor where the two orbital planes overlap. If that line I'm showing there, if that points towards the Sun, as it does here and here, you can see that a new moon now does have a shadow that is cast on the Earth. Or again, on the other side, there is a new moon and its shadow is cast on the Earth. So it's possible to stand on a point on the Earth's surface and have the moon block out the Sun. So we need not only to have a new moon. Remember, new moon is when the moon is between the Sun and the Earth. Full moon is when the moon is on the other side of the Earth. Not only do we need a new moon to have an eclipse, we also need to have the alignment of the Earth and the Sun and the moon coincident with this so-called line of nodes. These nodes that are the intersection of the moon's orbit with the Earth's orbit. Ideally, we also want this to occur when the moon is nice and close to the Earth, because then the moon is large enough in the sky to completely cover the disk of the Sun. If it's too far away, we will only get an annular eclipse and it won't cover the whole Sun. So how long does it take from one new moon to the next, or to get from one node back to the next node where an eclipse might take place? Well, here's a few numbers. If you really don't like numbers, then go and make a cup of tea and come back in a few minutes. A synodic month is the definition of how long it takes to go from one new moon to the next new moon, and that's about 29.5 days. But that's different from the so-called draconic month, which is how long it takes to go from one node back to the same node again. And remember, we need to be on a node in order to get the alignment we need for an eclipse. That's a different month. That's 27.2 days. And finally, remember, we want the moon to be close to the Earth if we want a total eclipse. If it's a long way from the Earth, it'll be an annular eclipse. And that changes because the moon's orbit around the Earth is an ellipse, not a circle, and so it will change. The distance of closest approach, so-called perigee, from one perigee to the next, again, is a different month, and that's called an anomalistic month. We won't worry about why they have these rather odd-sounding names. That's just the definition of the different months. So if we want an eclipse to occur and we want to have a new moon come round again, and we want it to be on a node again, and we want it to be as close as possible again, we need to ask ourselves, when, if we start at a particular point, do these months get back in sync again? They're obviously all different. If we wait 29.5 days, then the nodes will be out of kilter because they come round every 27 days. And similarly, if we wait 27 or 54 days, then the new moon will not be in the right place. It won't be a new moon because they come round every 29.5 days. Now, a long time ago, 5,000 years ago, something like that, the Babylonians realized that there's a particular relationship between these months. Again, we don't need to worry about exactly how they did the maths, but it so happens that if you look at 223 so-called synodic months, it turns out to be 6,585 and a third days. So what? Well, it turns out that a whole number of draconic months, 242 of them, happen to be 6,585 and a third days. By some sort of coincidence, a whole number of synodic months comes out to be very similar to a different number of draconic months. In other words, after this many days, if we start with a new moon that's lined up on a node, after this many days, 6585.3, it'll be back at a new moon position and it will be back on a node again. So if an eclipse occurs at a particular time of day, a particular time of year, after this period, an eclipse will happen again. It won't quite be the same distance between the Earth and the Moon, because the best we can do is to say, well, 239 anomalistic months, in other words, the month that tells you the closest approach to the next closest approach, that gives you 6585, but not quite the same fraction of a day. The difference between 0.32 days and 0.36 days is only about an hour or so. But after this many anomalistic months, notice we're off by a fraction of a day. It's not a big deal, but it means that the distance from the Earth to the Moon is going to be ever so slightly different. Now, 6585 days, I'm sure nobody's maths is good enough to figure that out, but that's about 18 years. So there's a period after which eclipses will repeat again. And this 18-year period, you notice, is not quite a whole number of days. It's about 1/3 of a day out. And we'll come back to that 1/3 of a day shortly. But we can at least say over this 18-year period, which many years ago was worked out and was called a Saros cycle, after 18 years, the moon's orbital periods, the moon's months, are back in sync with each other. So that means if an eclipse occurs, then if you wait one Saros period, 18 years, an eclipse will happen again. Two eclipses separated by 18 years will have a very similar geometry in terms of where the moon is, where the nodes are, and the distance from the Earth to the moon, and so the eclipse will be very similar, not necessarily identical because of this slight difference between this number and the other two numbers. But this 18-year period is very important for working out eclipses. If we try and represent that graphically, we can see when particular eclipses have occurred in the last 25 years or so. And we note that the eclipse that came across the UK in 1999 and just cut the corner off Cornwall, that was part of the same Saros cycle as the eclipse that happened in North America back in 2017. Those two eclipses are separated by 18 years, so the geometry of those eclipses was very similar. Also, we note that an eclipse that happened in 2006 is part of the same Saros cycle as the eclipse that has just occurred a few months back, again visible from North America in 2024. And I'll be describing a little later an eclipse I witnessed in 2006, 18 years ago, part of the same Saros cycle, a similar geometry of Earth, Moon and Sun. And just sort of so that we can visualize that a little better, we have to remind ourselves the moon goes round the Earth in an ellipse. This is a very exaggerated diagram, again, nowhere near to scale. The sun, of course, is much bigger and much further away, but just to give us an idea of what's going on, we can imagine the moon going around the Earth in an ellipse. In this particular case, we can imagine there's the line that joins the closest approach to the more distant approach of the moon. This point is called the apogee, and this point is called the perigee. For a given eclipse, for instance, at this point, we can say if the moon was at this point here, in between the sun and the earth, then an eclipse would take place. The moon is neither at its most distant point nor at its closest point, but it's quite a long way from the earth, so maybe this would be an annular eclipse. But 18 years later, the moon would be back in the new moon position, and the nodes would allow the shadow of the moon to hit the earth, but the ellipse of the earth would be in a slightly different position 18 years later. And notice that would mean that the moon actually in its orbit would be a little closer to the earth, so a total eclipse would last a little bit longer. And if we go forward another 18 years, the ellipse of the moon's orbit is in a slightly different position, and again the moon would be in a new moon position after one Saros, and it again would be a node, so the shadow of the moon would be cast on the earth, but again the moon is closer, so it would appear slightly larger in the sky, so the eclipse would last slightly longer. So as the 18-year periods clock on, we can calculate how large the moon would be in the sky based on its position in its orbit, and we can calculate how long the eclipse would be. And I'm not going to go through all of these details, but I'm including them here on the slide so that I'll make the handout of the slides available to you later. You can go back and have a look at these if you wish. There's the 2006 eclipse that I'm going to mention in a little while. If we go 18 years further forward, and then another 18 years, then another 18 years, etc., I don't think we're going to be seeing these eclipses, but you can see that they're all 18 years apart. And this is the size of the moon compared to the size of the sun, the diameter of the moon compared to the diameter of the sun as seen from Earth. So the moon is about 5% bigger than the sun. And notice that it's not quite the same each time. It's getting slightly larger each time. Remember the diagram I've just shown you? It's slightly larger each time because the moon is moving to a different point on its orbit, and because this number is getting slightly larger, so the length of the eclipse each time on this 18-year Saros cycle is getting slightly longer. So we're going from a 4-minute eclipse to something like a 5 or 6-minute eclipse over many years to come. Remember a little while ago I said the Saros period of 18 years, approximately 18 years, 6,500 and whatever days, is actually a third of a day at the end, 6585.3. There's a third of a day difference. So even though the moon is back in the right place for a new moon to cause an eclipse, in 1/3 of a day, of course, the Earth will have rotated 1/3 of a revolution. So a different part of the Earth will actually contain the shadow of the Earth. So one eclipse that's visible, for instance, from Asia, for one of these eclipses, 18 years later, 18 years with a third of a day, remember? That means next time a very similar eclipse is visible, but this time from Africa. Another third of a rotation, 18 years later, add a third of a day, now the eclipse is visible from the Americas. Go forward another 18 years, the Earth is now rotated approximately one revolution, 1/3 of a day, 3 times. So now we've got an eclipse back in Asia again, then Africa, then the Americas, then Asia. So we tend to get this cycling to different parts of the Earth simply because the Saros cycle is not an exact number of days, but has a third of a day left over. And so each eclipse visible each Saros cycle means that a different part of the Earth gets to experience the total eclipse. If we think about eclipses coming soon, I put this slide together a little while ago, so we're now running out of dates. So if we look at a few dates here, we've seen recent eclipses. For instance, 2024, we saw an eclipse fairly recently back in April, or at least those people, our cousins in North America, got to see it. Here we have the moon is about 5%, nearly 6% larger than the sun. So there was a quite long eclipse of 4 minutes, 28 seconds visible from North America. There are other eclipses coming up in 2026 and 2027, parts of different Saros cycles. You notice they're rather different. One is relatively short, one is relatively long, and they're visible from different parts of Europe. Unfortunately, not the United Kingdom, which is a bit of a shame. Rather than throwing lots of numbers at you, and for those that don't like numbers, I hope you've made your tea and you're now back with us again. One way of visualizing not the numbers of all of these eclipses, but asking where does the shadow actually hit the Earth, we can actually plot out the tracks of where the moon's shadow hits the surface of the Earth. So where are we? 2024, there's the eclipse that's just happened a few weeks back. It went across, where's this, Mexico and then Texas and then through a number of different states and then came out of the Atlantic. And then unfortunately the sun set before the shadow could arrive at the rest of Europe. There was an earlier eclipse in 2017 that also went through North America. They were lucky enough to get two eclipses a few years apart. And the eclipse I'm going to mention that I went to is this one here. In 2006, it went across Africa and then a little bit of Europe before heading across to Asia. This is all of the eclipses between 2001 and 2025, and you can see there are a number of them. It's not that unusual to get a total eclipse in any given year. It's just not always convenient to travel to where the eclipse occurs. If we move a little bit further forward and ask about eclipses between 2021 and 2040, they're now colour-coded. Blue means a total eclipse and red means an annular eclipse. Notice that there's a little bit of action now in southern Europe. Unfortunately, as you can see, nothing crosses the United Kingdom. But a couple of total eclipses and one annular eclipse do at least cross Spain. So for those of you who might want to try observing an eclipse, experiencing an eclipse for yourself, then it's a question of thinking about in 2026 or 2027 whether or not you want to travel to Spain to see one of these eclipses. You might ask, well, okay, I could travel to see one of these eclipses by travelling to where these tracks of totality are, but how long would I have to wait for one of these to come to me? In other words, what if we ask not about the next decade or two, but what if we have a long forward look? Well, if we go forward enough, then much of the Earth's surface is now covered with eclipse tracks. But notice what I've had to do here. I've had to take 1,000 years worth of eclipse tracks in order to cover most of the globe. And you probably can't tell, but I can just about see there's a tiny bit of green there where the cursor is pointing. That's Northern Ireland. So it looks like for the past 1,000 years, that little bit of Northern Ireland has never had a total eclipse over its soil. England has, you noticed, Wales has, Scotland has a number of eclipses over the last 1,000 years. But you see there are still a few gaps here and there. If you go back to, 1715 and 1724, there were actually two eclipses less than 10 years apart. These are the eclipse tracks. The ellipse there shows you the size of the moon's shadow on the Earth, and one of these eclipses ran across the country in 1715, and another one ran in a different direction in 1724. So there were some parts of South Wales, by the looks of it, Carmarthenshire, that would have had an eclipse in both of these years, less than 10 years apart. But unfortunately, we can't promise that in years or decades or even centuries to come. I wanted to experience the eclipse that was in the UK in August 1999. So I went down to Cornwall with some friends. But unfortunately, despite being clear the day before, it was cloudy on the day, and although I got to experience things getting dark, I never got to see the eclipse itself. I never got to see the corona of the sun. My friends and I were a little disappointed at that. We were all interested in astronomy and the idea of seeing an eclipse, so we planned the next one. and we realised there was going to be another eclipse 7 years later, 2006. There's an eclipse, and we figured that we did not want to spend too much of our money travelling the world to see an eclipse where there was a possibility of cloud. So we decided to go for this eclipse, which cuts across the Sahara Desert, which is not known for its cloudy conditions. There should be a pretty high probability of sun during the day in this region of Africa. So we thought, we don't often get this chance, so let's go for it. We checked cloud cover, and indeed the chances of cloud cover across the Sahara are minimal. It doesn't actually clip much of Egypt, it cuts through Libya. But at the time we were friends with Libya, so that wasn't a problem. So we decided to go for it. This was a picture taken during the eclipse, and you can clearly see the shadow of the moon here before it's entered Libya and then clips Egypt across the Mediterranean and then through Turkey and onwards. This little animation, this is genuine footage, afterwards of course, put together from a satellite looking down on Africa. A picture taken every few, I don't know exactly how many minutes between each frame, but you can see the shadow of the moon tracking across Africa, and we decided to try and intercept it roughly where the cursor is there before it goes out into the Mediterranean. Here's a map showing the track itself and roughly how long the eclipse will last, approximately 4 minutes for most of this region. It gets a little bit shorter as the shadow moves out across the Mediterranean, across Turkey, etc. But most people on this line would have got something like a 4-minute eclipse. So we were interested in a package deal of a cruise from Athens that took us across the Mediterranean to Benghazi and then take us to this point on the eclipse track. If we blow that up a little bit so we can see it in a bit more detail, you can see that typically there can be a lot of cloud over the Mediterranean, but the cloud tends to be restricted to the coast of Africa, and once you get inland it tends to be very clear, and the track itself was indicated by the black line. We decided to go for this point here. There's the track in more detail. The ship we were on berthed at Benghazi, and then we took the road into the eclipse track. There's virtually only one road that goes through the eclipse track, and so no surprise, that was the point that thousands of people converged on. People from all over the country and possibly neighbouring countries of Africa as well descended on this point, as well as a whole load of European tourists as well as American tourists descended on that point in the middle of nowhere to watch this eclipse. So we took the cruise ship to Benghazi, and then a whole load of coaches ferried us to the middle of the desert, where scientists had calculated that at a very precise moment the moon would perfectly cover the sun. So we set up the system. There's a couple of friends of mine and there's me, and we each had some cameras, both a still camera and a video camera, and we also had a video camera recording the experience itself. You're probably wondering why there's a t-shirt buried in the sand. That's because you see certain phenomena just as totality is about to set in. You see a certain interference effect called shadow bands, which I'm not going to discuss in detail, but I'll answer questions if you're interested. So I was taking pictures every few minutes. We got there just as the moon took a little bit of a nick out of the sun. So here I'm using a filter to make sure the sun isn't too bright for the photograph. And every few minutes, as the moon moves across the sun, I took an exposure, and you can see more and more of the sun being eaten up by the moon as it's just about to cover the sun. By this time, I was getting quite excited and just a little bit emotional as well, because I'd been waiting for this pretty much most of my adult life. I had read about eclipses since I was a kid, and this was my first chance to ever see one. So as the moon got closer and closer and closer to covering the sun, at some point you're thinking, is it going to miss or is it going to perfectly cover the sun? And of course, if you've got your sums right and the calculations have been done right, at the prescribed time, the moon just covers the sun. And then you get the so-called diamond ring, the last little bit of light, the sun poking out around the side of the moon. And at that particular point, you can start to see detail on the edge of the sun, a prominence there, a huge tongue of hydrogen coming off the surface of the sun. If we just blow that up a little bit, a picture taken a few seconds later, now the diamond ring has gone, but we can start to see detail, these prominences, these pink is the characteristic glow of hydrogen, these prominences on the edge of the sun, just before they get blocked by the edge of the moon. That was at 10:26. This, I think, was universal time, Greenwich Mean Time, not necessarily Libyan time. And we had 4 minutes of totality. So from this point onwards, we could forget the filters and we could enjoy the sight of the solar corona. And if we wished, we could use binoculars to look at the detail on the edge of the sun. And we had 4 minutes of that before finally the edge of the moon revealed the sun on the opposite side as the moon moves away. So you can see 10:30:44, some 4 minutes and a few seconds of totality. It really did go very quickly, but we knew exactly how much time we had, and we knew that the sun was going to return at a prescribed hour, so we could set an alarm to make sure that as the diamond ring showed for the second time, we could get our photos, and then the filters came back on again. But during those 4 minutes, I wanted to get the best picture I could of the corona. And the corona is very bright close to the moon's limb. In other words, the inner part of the corona is quite bright, so I used a very short exposure of 1/4000th of a second. This is with a camera sitting on a tripod. There's no need to track it because over a few minutes nothing much moves. I had a 300mm telephoto lens, and that's the picture in 1/4000th of a second. A longer exposure, you start to see more detail in the corona. And a longer exposure still, 1/250th of a second, you can start to see some rays, some structure in the corona, which are a result of the structure of the magnetic field of the sun. The North Pole is up here and the South Pole is down there. And these lines, you'll see in a moment, look very similar to the lines you see in the magnetic field of the Earth. But we know the corona goes further out than this, so I took an even longer exposure. But the problem is, although it's now starting to show detail of the outer part of the corona, notice that it's completely overexposed the inner part. And that's one of the problems with taking a picture of the corona. There's such a big difference between the inner and the outer brightness that one exposure might be good for the inner part and a different exposure good for the outer part, but none of these exposures, I wanted to go a little bit higher, I went to 15th of a second, a quarter of a second, they all captured a different part of the corona, but no single exposure captured everything. So I had to do a little bit of creative juggling with all of these images to try and combine them in such a way that I could capture all of the structure in the corona. And that's what I did once I got home a few days later. And that enabled me to get the picture that I really wanted, which is the beautiful structure of the solar corona. We see some structure close to the disk of the moon itself, and we see these wonderful brushes where you can see the North Pole magnetic field of the sun coming out on the north side, and similarly we see the brushes of the South Polar field coming out there as well. And we see these rays and streaks coming out towards the equator of the sun. Don't pay too much attention to this ghostly ring on the left hand side. That's simply an artifact. It's simply a reflection of the very bright inner corona taken with the longest of exposures, which was difficult to sort of take out of the image. In order to show a little more of the structure that's visible, that's roughly speaking, that particular image there is roughly speaking what the corona looked like by eye. Your eye is very good at adapting to different brightness levels, but in order to show some of the structure, which is difficult to see, it can be processed differently to show that there's an awful lot of structure in there. The magnetic field of the sun is wrapping around these prominences, and we get these sort of loops and arcs, as well as these brushes in the north and the brushes in the south of the sun's magnetic field. So it was an amazing experience, and it's difficult to explain just what it's like when the sun goes away in the middle of the day. This gives you an idea of the change of brightness level from normal daylight in the top left, images taken I think 10 or 20 seconds apart, something like that, just as the moon is about to completely cover the sun and get the diamond ring. So we've already seen the images of the sun. What I'd like to do now is show you a short video of a minute or so, taken with a camera simply sitting by the side of us as we were watching the eclipse. It gives you an idea of just how quickly the light levels drop, and it also gives you an idea of the experience of people watching the sun disappear. So let's have a look at that now. Still using the filters because the sun is quite bright, but in a few seconds we won't need the filters anymore. I hope that just gives you a little bit of the flavour of how excited people can get when they see a total eclipse for the first time. So my friends and I visited Africa in 2006, and it was a wonderful experience to see the animals, to see the culture of Libya, and to stand in the middle of the Sahara Desert and wait for the shadow of the moon so that we could experience the beautiful solar corona. If you ever get the chance, go for it. It's one of the few times that I can honestly say I was totally in awe of what I saw. Thank you for listening.